So here is the Viterbi algorithm which puts these ideas together. So the input to the algorithm is a sequence of words x1, x2 up to xn. The output is going to be the maximum value for any sequence of tags y1 through yn plus 1 of p x1 through xn y1 through yn plus 1. Now notice for now this is simply going to return the maximum probability for any sequence, and of course in reality we want to find the tag sequence that actually achieves this max. We want to calculate the argmax, in fact, but we'll see very soon how to do this. For now we'll just worry about the max, and we'll see on the next slide how a very simple change to the algorithm will allow us to actually compute the argmax. Okay, so we have an input sentence x1 through xn. We have these parameters q and d, which have typically been estimated from data, and then the algorithm proceeds as follows. Initialization step is to set pi 0 star star equals 1. Remember that was the base case of the recursion that I showed you. And then we have these definitions where s sub k is the set of possible tags at position k. So s minus 1 is s0 is equal to the star symbol, reflecting the fact that I can only have the star symbol at positions minus 1 or 0. And everywhere else sk equals s, where this is the set of tags. For example, we might have d and vp as the set of possible tags. So the algorithm is going to proceed to fill in these pi values, essentially left to right. So we go in order for k equals 1, 2, 3, right the way up to n, and at each point we apply this recursive definition. Okay, so for any position k, we consider all possible tag pairs u and v, possible at positions k minus 1 and k, and we simply compute pi k u v using this max over w's at sk minus 2. Recall this is the set of tags, possible tags at position k minus 2. And then I have this pi value times the q value times this e value. And then the only final step, remember we're returning the maximum probability for any tag sequence. The final step is to multiply in the stop probabilities. Okay, so we have a max over all possible uv pairs at the very end of the sequence at position n, and then we make sure to multiply in the stop probability q of stop given uv. This is just sort of a pesky little bit of bookkeeping we need to remember about. We need to worry about the stop symbol. That's what this final step does. And so that is it. That is the Viterbi algorithm. Okay, so as I said, our real goal is the following: to take as input a sequence of words x1 through xn and have as output argmax y1 through yn plus 1 p of x1 through xn y1 through yn plus 1. So here I've actually shown the full Viterbi algorithm, which makes use of a crucial idea from dynamic programming called backpointers to actually allow us to recover the argmax, to recover the highest scoring tag sequence. And it's actually a very small modification to the algorithm I just showed you. So the algorithm has the same inputs. Again, it has the same initialization point, and it's going to make use of these pi values in the same way as before, and the same definitions here. And we again proceed from left to right, k equals 1 to n for u and v. We calculate the pi value at each point. And the only change to the algorithm is that in addition to recording pi at each value of k, u, v, we also store a back pointer, which I'll call BP, of k, u, v. And that is the argmax. So that's actually going to record which tag achieved this max, which tag was most likely at position k minus 2, given the fact that I have u and v at position k. Okay, so this is just an additional piece of bookkeeping recording the argmax at each point. So once we've filled in these pi values and the back pointer values, we can actually find the highest scoring tag sequence by going backwards through the sequence at the end of this algorithm. So here's how this works. So after this loop is completed, I say yn minus 1 yn is the uv pair that maximizes pi n uv times q of stop given uv. Okay, so I've found the last two tags in the sequence. And then I go backwards through the sequence at each point saying that yk is the back pointer of k plus 2, yk plus 1, yk plus 2. Okay, so this is just unraveling the argmaxes to find the highest scoring tag sequence, and that's what we finally return. So that is it. This is the full Viterbi algorithm, which now makes use of back pointers to actually recover the highest probability sequence for an input x1 through xn. Let me just briefly talk about the runtime complexity of this algorithm. It is actually order n times number of tags cubed. So it's linear in the length of the sequence, and it's cubic in the number of possible tags in the sequence. How do we get that complexity? Well, so if we look at this, we have basically n times number of tags squared possible values entering this loop. Okay, so we enter this loop this many times, and at each point we have to do a search over s possible tags, and so we get an extra factor of s there, and that's how we get the n times s cubed runtime for this algorithm. So it is critically linear in the length of the sentence, and that is an absolutely enormous gain over brute force, which had complexity number of tags raised to the power n. We've gone from an exponential time algorithm to actually a linear time algorithm in n, and something which is cubic in the number of tags s. So that's a dramatic improvement.